All right, the time has come to talk about charges. Charges are going to be at the heart of what we're going to be doing for the next roughly 4 or 10 rather weeks. We're going to start off talking about what's called electrostatics. As you might kind of guess from the name, electrostatics is the study of the electrical interactions between still charges. Okay. Later we'll talk magnetism, which requires moving charges, and then we're going to go ahead and find some interesting connections between them. But at the core is always going to be charge. Now, what you're going to find the next several days is a lot of what we're doing initially is going to look a lot like what we talked about with gravity. This is the full Newtonian gravity. And there's going to be a lot of connections, and you can use a lot of analogies back and forth, so please be looking for them as we're going forward. But there are two really important differences between gravity and the electrostatic force. They really all stem from both stem from just one thing, which is that mass is mass. And that sounds like a stupid statement, but it'll make more sense in about a week. For now, the first point that comes out of that is that there are two kinds of charges, not one. Gravity just has that one kind of charge, and they all attract each other. In electrostatics, we have plus charges and we have minus charges. Okay? We weren't very creative when we thought of the names, I will have to admit. The plus charges are things like protons. There are other particles that have plus charges, but protons are going to be the main one you're going to find at the core of it. Negative charges are things like electrons. I will come back to that in a second, but I also want to point out that the charges were actually initially defined by the direction of the flow of current, which it turns out Benjamin Franklin coined or picked the convention for, and he actually got it wrong. You'll understand a little later when we get to it. I will point out what's wrong with it. It works fine the way it is. There's only one time when you can actually tell what's going on, what's different, but it is an annoyance for physicists and for electricians and electrical engineers and every single physics student when it comes to current later on. But for now, we have plus charges and minus charges. What's interesting about electrostatics and plus charges and minus charges, even before people really quantified what was going on, is they realized like charges repel each other. So plus charges repel plus charges, minus charges repel minus charges. But plus charges attract negative charges and vice versa. Okay? Gravity doesn't have this. Gravity always attracts itself. But charges have this repulsive capability. Okay? That's really interesting. The other kind of interesting thing about the way these charges interact is that as charges get closer together, the forces between them go up dramatically. Okay? Now, if you're really clever, you might even be able to guess what this rule for the force as a function of distance is going to look like. As a hint, it'll be very, very familiar looking. Okay? But as charges get closer together, they feel more and more force. So if you bring two positive charges together, for instance, when you try to do nuclear fusion, you've got to bring protons together to make the heavier helium nucleus. The protons do not want to get together. The closer you bring them together, the more they push each other apart. This is why you need really high pressures and really high temperatures, like in the core of the sun, to actually get fusion to even happen. You need those energies to basically overcome that repulsion and plow into each other hard enough to get close enough to actually bind together. Okay? Now, the other really interesting thing about charges is that there is, it turns out, a fundamental unit of charge. I'm going to put a bracket on this. It turns out that late in the 20th century discovered there are ways of breaking down this charge, or there's smaller units in places. They don't crop up anywhere that we're going to see them, and in fact don't exist for very long in nature ever. Only in particle colliders have we ever seen them. So there is basically a unit of charge. I like to write it as QE, which is the charge on an electron. It turns out to be the same as the charge on a proton. The electron is a more convenient label for it because the electrons are the more mobile ones, the one we kind of deal with the most often. Charge on an electron is 1.6 times 10 to the minus 19th coulombs. Coulomb is our basic unit of charge. Okay, it turns out a single coulomb of charge is quite a bit of charge. Okay? that means you've got an imbalance of 10 to the 19th coulomb, or 10 to the 19th electrons in something, which is quite a bit, as it turns out. The proton has the positive version of this, the electron has the negative version, of course. Okay? What's kind of cool about this is then this turns out to be the smallest unit you could possibly have, at least, again, for everything we're going to do. So nature has kind of decreed that things are going to step up in units like this. Now, this is very important when you're talking about ionizing atoms, for example. Ionized atoms will always have some multiple of this charge. Okay? As you get to more macroscopic items, these charges, you don't tend to notice this discreteness. I mean, if you have 1,979,403 of these, it's not very different from 1,979,404. You don't really notice, and so it looks like a continuous variation, which is why it took until the 20th century, or almost the 20th century, for somebody to realize there was this fundamental unit. The one last thing I want to tell you about charges is that charges cancel. If I've got something, say I'm made up of atoms, and I've got a mole of atoms. I've got 6.02 times 10 to the 23rd, helium atoms. Okay? I have zero charge inside of that collection of atoms. Now, in one sense, I have 6.02 times 10 to the 23rd negative electron charges, and I've got 6.02 times 10 to the 3rd positive proton charges. But because they're all so close together, they basically act as no net charge. Okay? Again, this is not something that happens with gravity. There is this sort of truism in physics that gravity is the weakest force. The two nuclear forces are strongest by most reckonings, the electrostatic force, and then way down they put gravity. I argue you can't really compare them except for in specific situations, because they work differently. But one thing I'm going to point out is gravity, even if you do think of it as being weaker than electrostatic force, it wins much of the time because it is so freaking patient. Gravity is always attractive, it's always there, and there's none of this cancellation stuff going on. So gravity just always sits there attracting things and gathering things. Whereas if you leave like a charged, planet someplace sitting in the universe, make it very charged for a second, it will pretty quickly, at least on astronomical timescales, become not very charged because if it's, say, positive, it'll start attracting electrons to itself. And every single electron it brings in will then start to reduce the overall net charge, then down to zero. So the universe, by and large, is not made up. When you look at the macroscopic size things, people-sized things and bigger, are not really charged for any appreciable purpose, as it turns out. Okay? So, this has been charges. This is mostly just a qualitative description. The only important number is this. You should memorize this number, or at least have it handy. I will give you a hint. It is not on your equation sheet. However, it is secretly on the equation sheet. There's something in there called the electron volt. And the electron volt is 1.6 times 10 to the minus 19th joules. Later on, we'll talk about why those two numbers are related. It's not a coincidence. But keep this number handy. This is the only quantitative thing so far. Tomorrow, we'll actually quantify the force law. Have a good day, and I will see you in class tomorrow.